Thanks everybody that joined. I'm Ido, and with me today is Amit. Hi, Amit.
Hey, Ido, how are you?
Not a day in paradise, my friend. Yourself?
Doing great, thank you.
Yeah. We're here today to talk about machine learning, data version control, and reproducibility at scale. A lot of words. I'm very excited about this one because we're going to cover a lot of things today. Just a few housekeeping rules. We have a bunch of people on LinkedIn. We have a bunch of people on Zoom. Those of you who are joining us on Zoom, you are anonymous here on the Zoom. Everybody's on mute besides Amit and I. If you have questions, please click on the Q&A icon and ask those questions, and we will answer them in writing and live. If you have questions on the LinkedIn side, then Karen from our team is actually on that LinkedIn, and she will translate the question so we make sure that we get everything answered. If you ask a question, keep in mind that you can do this anonymously or with your name as well, so your decision. So today's going to be a lot of fun. We're going to talk about ways. Well, I see that we already spun up the first question. So worth mentioning that Amit and I, obviously, as you can see with these with this cute axolotl here on the lower left, Amit and I are both with 𝗥𝗲𝒽𝒂𝒊𝒏𝒈. 𝗥𝗲𝒽𝒂𝒊𝒏𝒈 is the open source solution, which we will review throughout this call about how to utilize it for this version control. It is useful for us to know as we go over this, just in general, how familiar you are with 𝗥𝗲𝒽𝒂𝒊𝒏𝒈, so we'll know if we should spend more time on it or not. So there is a question that popped up for you right now in the poll. Are you familiar with 𝗥𝗲𝒽𝒂𝒊𝒏𝒈? If you can just answer yes or no. So we will see what those answers are, and we can behave accordingly. Thank you. Wait, 10 seconds, 9 seconds, 8 seconds, and to Mississippi. There you go. Let's talk about data version control for machine learning and why. And let's start with a day in the life of a data scientist. So, Amit, you and I speak with a lot of people in this space, and we kind of, I think, saw patterns over time. And kind of the story always begins with someone that has like a bunch of files somewhere on the cloud, right? Mm-hmm. And this can be annotation files and images files or Excel files. It doesn't really matter. There's like a lot of files that sit somewhere in the cloud, more files than what you will need for what you will use. I don't know if need for a training model. And very often, I see that people actually use, when they want to train their models, they use their personal computer. So the first thing that they need to do is they need to bring data into their personal computer. They either sample data, or they use a label solution to get a subset, or they take, I can have 200,000 images, but I'm going to use 1,000 for my model. So I'm going to go take those 1,000 emails, and then I'm going to train them on my local PC or my local strong computer with GPUs, and I'm going to create a model, right? And the first thing that we're going to speak about today is the need to version that data set. And when I mean that, what I mean by that data set is both the data and the code and the model and the model parameters. Everything together needs to be versioned in an easy way. Why? Because I want to be able to reproduce my data, because I want to be able to collaborate and share this with someone else. Because we have users that told us that they need this for auditing, right? They are required to show how they got to the models that they got to. And it's just like best practices in documentation. And I think more than everything, kind of the day in the life is driven with many, many experimentations. So what happens is that we version this data, or we train this model, even if we didn't version this data, and then we wait, right? We train the model, we wait for it, it's gone, and then we want to do this again. They want to do this again. There's a lot of waiting for my computer. There's a lot of copying, pasting, sampling, manual, trying to make sense of everything. And this is kind of, this is why this person is kind of, I guess, a little bit annoyed today. It's a little bit frustrating, and it's difficult to do this today. And the first thing that we're going to show you today is how to do this in a better way with 𝗥𝒲𝒃. 𝗥𝒲𝒃 is a data version control at scale that sits on top of an object store like S3, Azure, Google Storage, Min.io, and provides Git capabilities on top of that top of that object store. So imagine that you can take a bucket or a collection of buckets and you can branch, merge, rollback, and you can access different versions through your different tools like through MLflow or through your notebook, accessing 𝗥𝒲𝒃 and identifying the name of a branch or a commit identifier. A branch can be prod, test, dev, right? A commit identifier will be a single commit that includes maybe the raw data set, the cure data set, the model parameters, the model itself, everything that was used to train a specific model. So you can then go and access that in the future. And these Git actions, such as committing those changes, such as creating branches, can be done from a web interface, from the UI, from a command line interface, or from your notebook using code. As you can see here, I'm creating a branch in my repository, and we'll see that in the demo shortly. I want to remind everybody that if you have questions, feel free to ask them on the Q&A or on the LinkedIn chat. Now, how does this work? So as you can imagine, since we work on top of an object store, we have a lot of data that sits in a bucket somewhere, right? You have a lot of files sitting on your bucket. Every commit in 𝗥𝒲𝒃 is basically a collection of pointers to files that sit on top of that managed bucket. And then because the object store is immutable, meaning I cannot change this file, right? If I want to change it, I have to write a new one. So we do copy and write. So when a new file is created, the next commit will point to that additional file. But files that did not change, like this file over here, these files over here, you will have multiple commits pointing to the same physical objects. Why is this so powerful? Because we have thousands of users that we are aware of as an open source solution. I'm sure we have more. If I want to create a branch, that's a zero-copy clone. That's a metadata-only operation. It will be highly performant in milliseconds and will save a lot on storage because every experiment can have an entire copy of your entire data set. Every data engineer, every data scientist can have an entire copy of the entire data set without ever copying the file. And also you can go back in time without taking snapshots of the same files over and over again. Now, this is all nice and dandy, but we just started this conversation by talking about working locally, right? Like that point is, I want to have a local PC and I want to work on my PC locally. So how you did that with 𝗥𝒲𝒃? And this is actually a relatively new feature of 𝗥𝒲𝒃. I think it's been out for a month or two. One of the things that we developed is the ability to work locally with 𝗥𝒲𝒃. So imagine that I have a commit with or a branch or a repository in the cloud that's pointing to my files. What I can do from my personal computer is I can run a 𝗥𝒃 local command. And what this do is it will take the files that are a part of that commit or a subset of those files if I wanted to, and copy them over locally to my environment. And then often what we see is that people will actually modify these files, right? So maybe I want to change their size, maybe I want to add some annotations, maybe whatever I want to do. So let's say I'll take this file 5 and I'll change it a little bit, I'll edit it, right? And then the next time, when I actually commit those changes, 𝗥𝒃 will go and look at the differences, and that file that was added will be added to the managed bucket and will point to that additional file. So we have the ability to work with the object store remotely, but bring locally the files that we need, edit them, and then commit those changes back to the public cloud where everybody else can also get those details. I'll pause to see if there's any questions on the Q&A or the LinkedIn. So far, we're good.
Mm-hmm.
Okay, so we shared this before for those of you that were early. We're going to go through a demo today. We're going to use and Amit's going to walk us through it. We're going to use the 𝗥𝒃 server to spin up. We're going to use 𝗥𝒃 Cloud to spin up a 𝗥𝒃 server. You can also just run the open source version, and everything that we're showing you today is a part of the open source. You can run just a Docker Compose with 𝗥𝒃, or And on the other side, we have a sample repository that we're going to use that basically has a Jupyter notebook with everything that we're going to show you on this slide. We'll send this over at the end of this webinar, so you can try this up for yourself as well. For the demo here, Amit, I'll talk briefly about it and then I'll hand it to you. Okay. So for the demo here, what we're going to do is we took a blog post of someone from Databricks that was talking about a demo that created a demo for machine learning that basically detects ships in the ocean from satellite views. And what we have here is we have thousands of images that are sitting in a repository. The first demo that we're going to do is bring them locally, go through a pipeline, train the data, and commit changes as we go for complete reproducibility. So that's the first demo. And without further ado, I'll send this over to you, Amit.
Okay, let me share my screen. And also I'm going to hide my Zoom control to navigate easily. So if anybody asks any question, if you're not able to answer those, then let me know. I think you should be mostly able to answer those on your own, but if not, let me know. Okay, so either can you see my screen? Hello, Ido, can you hear me?
Yes, I can. I see a screen.
Okay.
But when I'm muted, you hear me less.
Okay. Okay, so let's start with the demo. First thing, as Ido mentioned, you need this sample repository. This demo, whatever I'm going to show today, is available on our Git repo for sample repo. So you can run everything on your own. So let's quickly look into that. So we have lots of different samples, but today we are going to focus on this a computer vision project for image segmentation. So and training the model to find certain things in images. In this case, we are going to look for the boats or ships in the satellite images. So if you want to run this as this sample on your own, everything is available here, the notebook, all the information, setup information here. For this, you also need 𝑩𝒓𝒆𝒂𝒄𝒉𝒆𝒔 server. You can spin up in the cloud very easily. It's a free for 30 days. And once you sign up, you'll get to this kind of view where in the clusters, you'll see your 𝗥𝒲𝒆 cluster is ready. So, and just click on that link and it will straight away take you to this 𝗥𝒓𝒆 server UI. So by default, you will have a sample repo in 𝗥𝒓𝒆 server on 𝗥𝒓𝒆 server. We also provide our own S3 bucket here for this sample repo. But if you want, you can use your own S3 bucket. There is a configuration required for cloud where you can connect to your S3 bucket if you want to. I'm not going to cover that here, but you can use this bucket also for testing your new repos. Let's say this is sample repo, but you can create additional repo in this by adding another folder within that. So that's on the just quick overview on how to set up on 𝗥𝒓𝒆 Cloud and 𝗥𝒓𝒆 Server. The next thing is for this demo, you need is the images to work on. So we did not post all the images because there are a lot of images here in this sample data set. And we are using Kaggle for this. And in Kaggle, there's a Airbus ship detection challenge. So Airbus, they had this challenge some time back. And they posted a lot of images, like around 200,000 satellite images with the boats in this. So it's a large data set, about 32 gig. So what you can do is just download this data set and upload into your S3 bucket. So in this case, this is my personal S3 bucket. So just have this folder inside this Airbus ship detection, and then upload all that data set, which you download from Kaggle. So that's kind of initial get up and running. Next thing is you will when you set up the sample notebook or sample container, here it will walk through all the setup instructions. It will create a local Docker container. So right now I'm already running this container. Initially, when you run this container, it will take some time to build the container. But once you have it, then you can easily start. It will take a few seconds to start the container. Okay, so now I have my image, this sample container running. And in this container, we have this notebook image segmentation. So that's what I'm going to use today. So that's kind of initial getting up to speed. Anything else, either I forgot, anything I missed?
No, but I didn't want to interrupt you. And there was one question on LinkedIn. So I'll call it out here and then I'll repeat it in answer. The question was a generic question about what happens when you use 𝑙akeFS. Do you have to exclusively use 𝑙akeFS? In other words, I will answer that, does the file structure and the underlying files change? And yeah, similar to using Iceberg, right? When you use 𝑙akeFS, the file structure changes and you need to access the data through 𝑙akeFS. However, it's not a rip and replace. You can easily enjoy both worlds. You can either use functionalities such as the import and export to easily bring things into 𝑙akeFS without actually copying them and create that translation, or exporting back to a regular file structure. And furthermore, 𝑙akeFS provides a generic S3 gateway, which allows basically anything that supports an S3 endpoint to connect with it. So often there's no need. So sorry for the quick distraction, just answering the question that came up in LinkedIn.
That's good. Thank you. So, okay, so let's walk through this notebook quickly. So here I'm going to just explain the architecture, target architecture we are going to use for this demo. As Ido mentioned earlier, we took the Databricks blog, which you can read on your own later. So what it provides in terms of architecture, we are going to read the satellite images as a binary data set, save that data set into Delta Lake as a Delta table, and then transfer that for training purpose using PyTorch Lightning to convert data set in the proper format so that PyTorch Lightning can understand that. We are going to use a library called PetaStorm. And this was open source by Uber. So this will convert data set in a format that PyTorch can understand. And also you can run that. It will work with the GPUs also. So it will convert into a format which will work for CPU as well as GPU. And then once we do run the training, when you run a lot of experiment locally or in distributed computing environment or in the cloud, we are going to record everything in MLflow, all the experiment logging, and what's the output of parameters used for that training, what's the output metric for this model, everything will be recorded in MLflow. So that's the very high level architecture. I think Ido talked about this, what we are going to show today. So first I'll start with the local experimentation. So let's get started here. In this notebook, we have three sections. One is configuration initially, and then setup, and then running the actual demo. So let's start with the configuration. Here you'll specify the endpoint to connect to the 𝑙akeFS server. As I mentioned earlier, I'm using 𝑙akeFS Cloud today. So this is my endpoint here, which you can just copy this from here. And then you have the 𝑙akeFS access key and secret key. So you can go and create your access key and secret key. Just go to the administration and then click on create access key. I already did this in advance. So this is my access key and secret key. So I'm going to set those in the variable in this notebook. Then you specify the repo name. You don't have to change the repo name, but if you want, you can change the repo name. Next thing is when you create the 𝑙akeFS repository, you specify the storage for 𝑙akeFS repository, not for your data set. Data set can be in a separate S3 bucket, but this is where the 𝑙akeFS repository will sit. And this, you can use your own S3 bucket, or you can use the bucket provided by us, as I mentioned earlier. So this is the bucket we provided here. So you can just copy paste this URL and then add the repo name at the end, or you can add another folder name inside this also. So you can use our bucket to create the 𝑙akeFS repository. So that's what I'm going to do today. Next thing is when here there's a variable whether to specify whether you are running this experiment locally or in the distributed cluster environment. So right now, initially, I'm going to run this locally. So specify that variable here as local. For local training, I'm going to use a smaller data set. I mentioned earlier that data set has about 200,000 images, but I'm going to use just the 100 images initially on my local, so it will run fast. And then we can scale up to as many images as you want in the distributed computing environment. Next thing is the demo data set I talked about, which is on Kaggle. So as you upload into S3 bucket, you will specify your bucket name here and the region where it is stored and in the folder where it is stored. So this is my personal bucket here. And the access key to AWS access key, not the 𝑙akeFS access key, but the AWS access key to connect to that bucket where your data set is stored. So that's everything in the config part. All these things we are storing as a variable, which we'll use it further down. Next thing is the setup. For setup, I'm going to just run this additional notebook. We have separate setup notebook, which has imports the libraries required for this demo, any functions, the helper functions that we need. It will also create the repositories. So as you see here, it just creates this repository in 𝗥𝒽𝒻. So if I go back into 𝗥𝒽𝒻 UI here and just refresh this. So now we have this image segmentation repo. Again, as I mentioned earlier, this is using our S3 bucket with the subfolder inside that with the repo name. So far, this repository is empty. There's nothing in there. So what we are going to next is import the data set into this repository. But we are going to also show the integration of 𝗥𝒽𝒻 with Git. So when I'm running locally, I'm going to create the Git repository. So first we created the 𝗥𝒽𝒻 repository. Now I'm going to also create the Git repo locally. So you'll see it in our container. It will create the folder for Git repository. So let me just create the Git repo here. So I have my repo here. And also if you go into your Finder or the file browser, so you will see that also, that Git repo also available locally also. So now I think I have done all the setup part. So we have the 𝗥𝒽𝒻 repository ready. We have the Git repo ready. And now we'll start the main demo. But before I go further, anything else either you want to mention, anything I missed?
See if there's any questions. I don't think you missed anything. I think it's fantastic to see that we have everything written if someone wants to try this out. So the Git repo is going to store the code. 𝗥𝒽𝒻 is going to store the data. And somehow we're going to connect these two together.
Correct. That's what I'm going to show next. Okay, so what we are going to do is we are going to create an experiment branch in 𝗥𝒽𝒻 as well as in Git repo. And if you're running this experiment multiple times, you can just increment the experiment branch number here. So we are just going to create a local branch here in the Git, as well as the branch in 𝗥𝒽𝒻 repository by using branch creation for 𝗥𝒽𝒻. So if I go back here under my branches, now I have my local experiment one branch in 𝗥𝒽𝒻 repository, and also on Git, it switched to this local experiment one branch. Next thing, what I'm going to do is just read that data set. I mentioned earlier that satellite images, we have about 200,000 images, so which is stored on S3. So right now what I'm doing is going to get the list of all those images and then randomly select 100 images in this case for my local experimentation. But a lot of time people use the labeling tool to select those images. They don't just randomly select images, but based on certain criteria or certain labels, you might select certain images for your training purpose, or somebody might provide you a list of images to use for your training data set. That's what you can bring and then import into 𝗥𝒽𝒻 repository. So right now it's just going through the list of images in S3. So it's taking a little bit of time. So now it's done. So it's about 200,000 images. And then I'm going to just randomly select these 100 images for my experiment. And you can change this number of images required for experimentation. This was just the initial setup I did for 100. Next thing, I'm going to import those images into 𝗥𝒂𝒃 repository. While this thing is running, the import process is a zero copy operation. So we are not copying these images from the S3 bucket to 𝗥𝒂𝒃 repository. We are just creating a pointers to those files. So even if you select 1,000 files, 10,000 images, this import process will be very quick. So if I go here and look into my branch, go into this branch in 𝗥𝒂𝒃 repository, I have this raw data set now with the images. And in this case, I just imported the 100 images. So, and also the image mask. The image mask is stored the information about the ships in those images or boats in those images. So if I go into this data set, this is all images here, which we imported into 𝗥𝒂𝒃 repository. So just quickly look into those, one of those. Yeah, I don't see any boats here.
Another lot of ships here.
Yeah, a lot of images don't have any boats or ships. So we are going to filter those images also, which don't have any boats or ships. Yeah. And also just quickly here, specify about the object. If you go into object info, as you can see here, this image is pointing to this file on S3 bucket. So we are not making a copy. We just have a pointer to that certain file. Anything else, Ido, you want to add?
Yeah, just to call out, again, for that question that was asked, I opened it on the side here by Yusuf on LinkedIn. So this is an example of how you'll probably have, this is common. It's not the only way, it's one of the ways, but you can have something that constantly kind of writes the images and the input at one place. And then when you come to do your experiment, the first thing that you do is you import that data set into 𝗥𝒂𝒃. So of course, whatever writes does not need to be familiar with 𝗥𝒂𝒃 because we're just going to create those pointers in a zero copy import and work with the data set as it sits in place.
Good, thank you. And I think I forgot one more thing while doing the demo, the question, but the poll, I'll come back to this when I'm running this demo. When I have time, and I will ask that question also. Okay, so now I have my images imported into 𝗥𝒂𝒃 using zero copy operation, zero clone copy. And next thing is I'm going to work locally with this data set. So I'm going to just set up some variables here if I'm working locally versus in the distributed environment. When I run in distributed environment, I'm going to read directly from the repository, but for local, I'm going to copy or download those images locally. So as Ido mentioned earlier, we recently came out with this feature. 𝒥CTL is the command line interface CLI for 𝗥𝒂𝒃. And then we have added this local functionality here where you can clone everything locally, work locally, commit your changes to the 𝗥𝒂𝒃 server. So I'm going to just clone this branch in this case. So I'm going to clone my repo and experiment branch in that repo to a particular path here. So this is my path here, which I am specified here. So I cloned all these images inside this Git repo in this particular folder. So if I go here, all these images are available here also. Let me try another one. This one also doesn't have any boards. So now I have all my files locally inside a Git repo. One thing I want to mention how we work together with Git. So we are going to use Git to version control your code. In this case, it will be these notebooks, or it can be any Python, Spark program, whatever code you have. You will use Git for version controlling that, and 𝗥𝒂𝒃 for version controlling your data. So when you clone this, all these images locally inside this Git repository, a lot of time people ask the question, now if I commit my changes to Git repo, it's going to commit those lots of images also, and Git doesn't support the big data. So what we do is when you clone this 𝗥𝒂𝒃 branch locally, we add that particular folder in the git ignore file. So Git is going to ignore any files inside this folder, in this lakeFS local folder. It can be any folder name. I just specified this as a variable here. But it's not going to ignore this YAML file that we create. And that YAML file includes the information, lakeFS commit information. So in this YAML file, for example, we have this source, which includes the lakeFS repository name, the branch name, and the commit ID. So this is basically it tells you that for a particular, let's say when you commit your changes into Git along with your code, it's going to commit the YAML file, which includes all the information about the lakeFS commit for your data set. So then that way you have code plus data together in a single commit in Git. And also this commit ID is basically here. If you go into lakeFS and look for these commits, so you'll see this is the same commit ID as this one after importing your data set images initial. So that's how we work together with Git. So now, next thing what I'll do is, let's look into like whether we can read this data set, which is locally using Spark. In this case, I'm just read these images in the Spark data frame and to guess the width and height in this case, for example. So you can see we have all these images and it's reading locally. This is my container path here, and this is my local folder inside this. So that's what I'm going to use for my training the model, everything locally here. Next thing, I'm going to build my data pipeline. I think this will take about a few minutes to run, 4 or 5 minutes to run the pipeline. We are using Medallion architecture. I'll explain everything, but let me run this pipeline. So it runs in the background and I can explain everything. Okay, while this thing is running, let me also ask a question to our audience while this thing is running, like what kind of technology stack you use, like what are you running in the cloud, your experimentation, are you running locally, are you using Databricks, a Spark cluster, are you using any orchestration tools, labeling tools? Please go ahead and answer those questions. And while this pipeline building is running, we have some time here. And I will also explain what I'm doing in this pipeline. Okay, so a few seconds more for people to answer. And now I'm going to end the poll. Okay, so let me explain what's going on in this pipeline. So let's go back to this picture. So what we did is initially we took these images, satellite images, about 200,000, download those about 100 images in this case for my local experimentation. Read that and convert into a delta table. So read as in the binary format, convert into my bronze data set. So we had raw data set. After converting, it's a bronze data set. So we are, as I mentioned earlier, we are using the Medallion architecture in this case. Then we are going to enhance our images, resize those images, as well as transform the mask into images. So mask, as I mentioned, it's a CSV file. That mask tells you the location of the ships on this images, if there are boats or ships in the image. So it will tell you the location information. So we transfer that mask into also images and can save this as a silver data set. And again, all these data sets are getting stored in lakeFS repository. I'll show you that in a second. And then we take that silver data set and join the images with the mask. So we have these satellite images, and then we have masking information where the boats are in those images. We join those together to create the gold data set. And that's what you see here in this picture. So for example, for this satellite images, there are 2 boats here or multiple boats here. They're hard to see all the boats here. So we will count also the number of boats. In this case, this image has 4 boats. And here also, this one also has 4 boats. So that's what right now we were running in this pipeline and saving everything into lakeFS repository in different different data sets like bronze, silver, and gold. So if I go back to my lakeFS repository for that particular branch, the local experiment branch, So now I have my raw data set, my bronze, silver, and gold data set. Everything is saved in 𝑙akeFS repository for version control purpose. And also we tag it. So in future, if you want, you can look for the data set using the tag instead of using the commit ID, because commit ID is a long ID. It's hard to remember. So you can put the tag also, any way you want to use the tag. It's up to you. So that's what I did in my code. I tagged also all my data sets. Okay, so my pipeline is done. All the transformation images, everything is done. A lot of work required, like a lot of people spend time to transform all these data set in different format. And it's always good to version control that for future reproducibility purpose. So that's where the 𝗥𝗲𝒽 comes into play to version control all these data sets. We are not going to version control this in Git repo. Everything is version control in 𝗥𝗲𝒽 repository. So here also, if I look into, I have all this data set locally, as well as my data set on the server itself. So I commit all the changes, all the transformation I did into 𝗥𝗲𝒽 repository also. And as you can see, this is like just randomly selecting those 100 images and then going through the process and then creating this gold data set, which have mask information as well as the images and how many boats or ships are there in each images. And also when we do this, we remove all the images which don't have any ships. There are a lot of images which don't have any boats or ships, so we exclude those also. So we have a good data set now. Okay, so before we train the model, anything else either you want to add?
Yeah, just one thing. There was a question, is it possible to create a tag related to an older commit and not just point to the last one? The answer is yes, just to make sure that we call it out over. I can tag any historical commit across any branch at any point in the next set.
Mm-hmm. Okay, so now my data set is ready. Now I'm going to use it for training. So next thing, I'm going to randomly split this data set into a train and test. So normally people use 80-20 rule, but you can use whatever rules you want. So in this case, I use 80-20s and then split those into a training data set and the test data set. Okay, the next thing, as I mentioned earlier, we are going to use the datastorm library to transform this gold data set in a format that PyTorch can understand. So in this case, this also is happening locally here. It is storing this information in the datastorm cache. In case of distributed, you can store on the local servers and the distributed environment. So in this case, as you see here, now we started with 100 images, but now we are left with 13 images in the training data set and 3 in the test. So a very small data set locally when I'm training. So after removing all the images which don't have any boards, we are left with about 16 images now. Next, I'm going to train my model locally. So in this case, we are using this image segmentation model. It's publicly available. And that's what library we are using here. It's in the code here. I'm not going to go into too much on the ML code, but that's what we are using. So once we train this model, it gives you the output for the metric which you are using to measure the performance of this model. Again, this is a small data set, so you may not get very good output from this. So that's where we are going to train this model in a scale, still using 𝗥𝗲𝒽, everything same data set, and then we'll train this model in a scale on in distributed computing environment also. So once you train this model, after this is done, you might run this experiment multiple times, so you can create multiple branches here. I did just one branch, local experiment 1, but you can run this model or this notebook multiple times by incrementing the branch name and run the same process every time with different image set. So you can, initially I started with 100, you can go with 500,000, whatever you can afford to run on your local laptop, and then create another branch and train the model again with different image set. And then we are recording all those model training experimentation in MLflow. So let's look into the best model that we got. In this case, right now, I just did one training, one experiment. So it's going to just tell me, oh, this is your best model. But in real life, you will run it multiple times and it will select the best model based on the metric value. And then you can store this best model information in 𝑩𝒓𝒆 repository. And let me commit this and I'll show you how it looks in 𝑩𝒓𝒆 repository. So let me go here in my branch here. So in 𝑩𝒓𝒆, we are just keeping the data set for version control. The actual model will be stored in MLflow artifact. I'll show you that. But we are including the best model information in 𝑩𝒓𝒆 repository for linkage purpose. So this will tell you where the artifact is stored, that model is stored, what was the run which you ran, what time, and what metrics you used. Sorry, what's the parameters you used, what was the output metric output was. And there are a lot of tags we add when we're running this model. And I'll show you some of those tags later. So that tag information is also stored in this particular file. Okay, let's go back here. Next, once let's say you train the model many times and you want to select the best model and make it production ready. When you run in distributed environment, you might run lots of models in parallel, train the models in parallel, and then select the best model and make it production ready. And then next thing I want to show is about going back to the integration with Git, how it looks like. So what I'm going to do is use Git to version control my data. So these are my notebooks, which has all the code. So I'm going to I just copied those files into my Git repository here. So these are my two files or two notebooks that I'm going to version control in Git, but not the data set. So if you see here, when I add my files into Git staging area and just check the status, you can see here, I'm going to version control these two notebooks using Git and the YAML file, 𝑩𝒓𝒆 YAML file, which has the 𝑩𝒓𝒆 commit information. So that way you have all the information together here. So like this is my code and this is my 𝑩𝒓𝒆 commit information. So you can go and look into 𝑩𝒓𝒆 to get the data set for that at that time. So that's how you do the integration between Git and 𝑩𝒓𝒆. Okay, so I think I covered a lot before I go into MLflow side. Anything else either you want to add or mention? Anything I missed? Any questions?
No, this is a lot. See if there's any questions. I know that in this one we're really jumping quickly because we still have a lot more to cover. So
okay,
okay, yeah, let's continue. Let's look at MLflow and the integration with the data version control.
Okay, so this container also includes MLflow. So everything is packaged in this single container. So let's start the MLflow UI. So this is another notebook here. We just click on that notebook, start my MLflow UI here, MLflow server, and then go to MLflow UI. And as you will see this, I just ran this training just 5 minutes ago. This is the experiment run. And I'll come back to this. Next, there's another last cell, you run this and it will give you the link to go to the commit information on 𝑩𝒓𝒆. You can find directly in the UI, but it will tell you, just give you a link to go to the commit. So if I click on that, it will take me to the commit for the information we saved for the best model in 𝑩𝒓𝒆. So here, as I mentioned earlier in this, it has all the information in the metadata also we are saving here. Like what was the model name, what was the run name, what model version we used, and what was the output for this. You can include any metadata you want, including the parameters also, but parameters are saved in MLflow too, and in the best model text file. And from here, it will also take straight to this model run, particular model run. So this is the register one. So if I go into click on that link, it will straight away take me to MLflow, this particular experiment. And if I click on this run includes all the information regarding this model training, including this pickle file for model, as well as the data set which was used to train this model. So this is my data set, the gold data set. And in this case, as I mentioned earlier, we used a very small number of images, 16 images. There was 13 for the training and 3 for the test. And this is the fields and the data types for that particular data set. It also includes the parameters you used. In this case, we just used these 3 parameters, the architecture and the encoder and the learning rate to train my model. Then the output, matrix output, the loss, as well as the intersection union intersection over union metric for computer vision purpose. Then all the tags, we include a lot of tags here. For example, what was your 𝑙akeFS repository? What was your branch name or the tag? Also, you can include and the data set, which was used to train this particular model. So if I take this data set URL and open this in a browser here, it will straight away take me to the data set which was used to train this particular model. This is my gold data set and with the particular tag here. So straight away it will take you to the data set it was used to train this model. So everything is stored together. So now I think that's pretty much on when you're running locally. Next, you want to go back to your presentation?
Yeah, so we have 13 more minutes and we have some amazing, one last thing, as they say in Apple, right? That we think is really a game changer, which is everything that we spoke about until now. We're saying, okay, let's talk about the day in the life where I work locally, right? But in life, you don't only have the storage in the cloud, you also have compute in the cloud. And the idea is maybe to, on your desktop, only run a notebook, any notebook that you like, right? Any flavor that you want. And basically, instead of copying files, working locally, and so on, have that notebook point to the cloud compute and then just run everything that we just did right now with on a cluster that runs on the cloud and version it the same way that it did it now. And the advantage of this are, I don't have to copy paste. I can use a much bigger data set. This is better performant because the cloud compute is going to work directly with the cloud storage. And I also don't have to wait. So I can do this concurrently as much as I want. I can just get this larger GPU machine on demand from the cloud and run, instead of 1,000 images, run on 100,000 images or 10,000 images. There's just a much better scalability here and the way to work with public, utilizing the compute on the public cloud and work with distributed compute engines such as MLSpark, for example. So let's see what that looks like.
Okay, let me share my screen. Don't have enough time, so what I'm going to not run the whole notebook again in distributed environment. So for this, I'm using Databricks cluster, but you can have your own Spark cluster and then the same notebook in your Spark cluster. So what you will do is you will just take this same notebook and import. In this case, I import it into my Databricks environment and ran this ahead of time. So a couple of changes you will make here. First is in the initial configuration part, just change this variable to distributed from local. So when you, and also increase the number of images. In this case, I'm using 1,000, but you can use 10,000, whatever you want to use, depending upon your cluster size. So these are the 2 changes you will do. Rest of the things remain the same as is. So let me quickly show you one thing here. When you are running a distributed environment, it's going to read the data set directly from 𝑙akeFS server. All the pipeline work, everything will be saved again in 𝑙akeFS repository. So if I go into my 𝑙akeFS repository and for distributed experiment, if I look into that branch, when you run all this pipeline, everything, you have your raw data set, all your bronze, silver, gold data set. And so that's will be a go straight to the 𝑙akeFS repository. And when you are reading all your data set also, I'll just quickly show here. When you read from in the distributed environment, it's reading from the 𝑙akeFS repository directly. So in case of local, I was reading the files locally and running my experiment, but in this case, it's reading from the server. The advantage with that is you can scale up much higher. You don't have the constraint of your the local disk space here, because it's reading directly from those images from 𝒐𝒏𝒆 server, which basically points to the physical file in your S3 bucket. And then we create this data frame and then work on this. So that's the advantage of running in the using 𝒐𝒏𝒆 server directly. And once you're done running this, again, you will train this. In this case, I'm going to train this model by using multiple parameters and fine-tune those parameters. So as I mentioned earlier, there are 3 parameters: the architecture, the encoder, and the learning rate. So here you specify different types of architecture, different types of encoders, and the different values for learning code, and run this in parallel. And when I was running locally, I was using parallel of 2, but when I'm running in the cluster, in this case, I'm using the cluster workers, how many workers I have in Databricks, that's the parallel process I'm running. And here also you can specify how many runs you want to do. So in this case, I'm doing 3 runs, but you can go up to 20 or as many as you want based on your compute size. And once it's done, it's going to store the best model in the repository, in 𝒐𝒏𝒆 repository, and all those things you did locally, everything is same here, but not reading the file locally. It's reading from the 𝒐𝒏𝒆 server. And in this case, for MLflow, if you have used Databricks, it's stored, the information is stored here in the model. So if I go into my model here and go to this particular model here and go to this production version, the last version, and look at for this particular run. Again, all this information which was available in local MLflow is available on Databricks cluster also with all the tags. Here I'm using this distributed experiment branch. And again, this is the URL for the datasets. Again, I can just copy this data URL and it will straight away take me to that dataset which was used to train this particular model. So again, we are keeping everything together. So far what we did, like we are version controlling our code in Git, version controlling data in 𝒐𝒏𝒆 repository, and then version controlling, keeping all the model and experiment information in MLflow, and everything is tied together, linked together. So that's what we had in the demo today. Okay. Yeah,
that's pretty incredible. Let's see if there's we passed through a lot. So I think what we talked about is first, the day in the life, how to work locally if that's what you want, if that's where your GPU, and actually version control your data sets with synchronizing them against the bucket in a very transparent way. And right after that, we spoke about how to do a day in a better life, as we called it, right? How to do this in a way that works directly with the object store, which scales better, easier to use, and you can take advantage of more tools out there as well. Now, the outcomes of 𝒐𝒏𝒆 are pretty straightforward. I'm gonna, if we can post the last question of if this was helpful, just to kind of know where we stand, and then I'll share some links right after that. It's really interesting for us to know if it's helpful. So I'm asking those of you who are on Zoom, I'm asking you if this was very helpful, or maybe it was just interesting but irrelevant, or maybe it was a complete waste of your time. I don't know. It's helpful for us to know so we can plan for future sessions accordingly. Again, the outcomes of �𝒏𝒆 are pretty straightforward. It's a faster time to market, right? It's things that we have users that talked about 80% reduction in testing times. There's no risk whatsoever. There's always the ability to roll back. There's tremendous storage savings because everything is zero-copy clone. And of course, I think the most obvious thing from this call, it's a full reproducibility on your ML testing with an engineering best practice way. So that's kind of the outcome of that, kind of what we want to talk about today. And everything that Amit and I show today is a part of the open source. Like, this is open source with an open core approach, meaning there's no artificial boundaries in place, right? But there's no up to 5 pipelines or things like that in the open source solution. We do have a hosted solution, a SaaS, solution, 𝑙akeFS Cloud, as well as an enterprise solution where you run 𝑙akeFS by yourself. In both cases, you get enterprise features such as SSO and RBAC, but with the SaaS solution, which is highly secured because the data always sits in place anyway, you also get the benefits of the SaaS solutions, right? We patch it, we maintain it, we scale it, and so on and so forth. So that's what we reviewed today. What's next? Again, we have a tremendous Slack community. So it would be really, really nice if anybody here right now will just immediately go to https://lakefs.io/Slack and join our Slack community. Amit is there, I'm there, our entire team is there. There's a help channel there that can help anybody that gets started. Please don't hesitate twice by asking questions there. Would love to see you there. We had a nice amount of people here on Zoom today, and a decent amount also on enough on LinkedIn also, by nature. Yeah.
And also the good news is on the poll, that last question, like 100% people responded back. It was very useful. So I'm happy to see that.
Okay, that's fantastic. That's good to know. You have 𝑙akeFS Cloud. If you want to spin up 𝑙akeFS, you have the sample repo. We created like a shorter URL here to that GitHub sample repo. We'll wait 20-30 more seconds to see if anybody else has questions before we carry on. Yeah, there is a question. I'm querying Parquet data with filters through 𝑙akeFS using Dask with Parquet, and everything is working like a charm, but how does it work? Is 𝑙akeFS able to get just the file needed before answering, or does it need to get all the data from the buckets on the machine where 𝑙akeFS is hosting the filter? Since we are data stored on S3 in a different format than Parquet. Okay, this is kind of a complicated question. I'm not sure I completely answer it. I mean, do you read this question as how does the client work?
Yeah, so normally, if you know, like we have a 𝑙akeFS client where you read directly from your storage. So you don't go through the 𝑙akeFS server. So you are not dependent on, the data is not flowing through the 𝑙akeFS server. So anytime you do, whether you use 𝑙akeFS server or not, whatever it works, it will work the same way. Data is not flowing through the 𝑙akeFS server if you use 𝑙akeFS client, which we use for this demo also.
Yeah, I think yeah, there's two ways to work with 𝑙akeFS with Spark specifically. So I'm assuming that's relevant here. One is with the 𝑙akeFS client. The 𝑙akeFS client, the data flows from your notebook to your object storage without going through 𝑙akeFS. So it will first ask the 𝑙akeFS server where's the location of the files, and then it will work directly with the data. The other way is with an S3A gateway. Regardless, in both cases, we don't actually query the entire data, right? We take advantage of whatever querying system you use, and just the relevant files are asked using 𝑙akeFS. So if you kind of look at the API calls of 𝑙akeFS, the number of those API calls will be similar to the number of end calls that you see in like an S3 on the other side. Okay, see if there's any other questions. Okay, in that case, pause, going once, going twice. Amit, thank you so much.
Thank you. Thanks for your time too.
And thank you everybody that joins today.